Hello and welcome to this lecture on KMeans hands-on. We'll go into Scikit-Learn and working with KMeans, the unsupervised learning. This is the first video where we'll go into unsupervised learning tutorial hands-on. Here I will actually do some simulation of data. You'll see how that looks like. We can visually try to understand how K-means work and how unsupervised learning works. This will be quite interesting. We won't take any dataset from the web. Instead, we'll go directly into Visual Studio Code, setup, and do working with Scikit-Learn to simulate data and then working with that. Let's go into Visual Studio Code. Here I am in Visual Studio Code and we'll start with creating a virtual environment, uvven source.ven bin activate, and then uvpip install scikit-learn, pandas, matplotlib, and seaborn, ipykernel to work with Jupyter Notebook. This should be it. Install this and it's done. Now let's create our Jupyter Notebook, kmeans.ipnd. Here I will call this KMeans, and we change this to Python. Yes, this is my environment, and we start with simulating some data. We'll use sklearn.datasets, import make blobs. This is quite interesting dataset. This is quite interesting when you're working with it. You can use this to simulate blobs. I'll show you how that is. X, y equals to make blobs, and I will have 500 and centers equals to 4. We have 4 centers, and we have random state equals to 42, and then we have cluster std equals to 1. I'll show you what that means. We'll see. We will take a look into, we'll do df. We'll take a look into x. It looks like this. This is array. You can take its x.shape, and you have x from, it's 500 rows and 2 columns. It's what we expect, 500. Since this is 2D data now, we have 2 columns. Then y, how does that look like? It's a different target. You can see it as different classes. y.shape, it's 500 also. You can see it as we have x, y. Or we have the target. We have, for example, let me take an example here. x:5, then this is the first 5 rows of x. We can see y:5. We slice to 5, and you can see here the first one has label 3, the second one has label 2, and then 1, and then 0, and then 2. Okay, this is how these variables look like. What we can do is that we can do a data frame now. df, let me import pandas. So import pandas as pd. And then we have df equals to pd dot data frame. We can have here x :0. We take everything from 0, and then we take x :1. We take everything in first column and then the second column. Then we take here y. Then we can look into df. It looks like this, and we'll do .t to transpose it. We have 0, 1, and 2. Then we can take a look into, we can do df.columns equals to x1. We can have feature x2, and then we'll have y. Okay, if we take a look into df.head, now it looks like this. We have x1, x2, and y. This is starting to get similar to when you're importing data from CSV and you have different column features here and you have a label. This starts to look like that, and we can make actually the y, we can call it label to make it more descriptive. We can do, you can see it's float also. We can make it into, we can do df label as type int, df of label equals to this one. Okay, this one becomes integer. Now, when we have this, we can plot this. We can do import seaborn as SNS, and then we can do sns.scatterplot data equals df, x equals to x1, and then y equals to x2. And if I do this, we can see that we get scattered data here. You can see that they are in different clusters. And you can have here x2, we can have hue equals to label. You can see this is the label and it's quite ugly. We have another palette here, tab 10. Yeah, this one looks better. Okay, what you can see from here, I will explain a little bit about if we take a look into the standard deviation here. If we take it in 10, for example, and we run all, then the data is more spread. You can see it's very spread out here. But I will keep it simple and keep it as 1. You can see that then it's more grouped together. This is to make it a little bit simpler to visualize. But you can take and play around with different values of the standard deviation. This is the original data. If we call x equals this one, then x.set title, let's see, original data. Now, when we have this, can start to drop our label, since remember that we don't have a label, right, in unsupervised learning. In unsupervised learning, we don't have a label. X equals df.drop. Here I will drop the label, and x is equals to 1. Then we can take a look into x. Let's see, y, it's called label maybe. Yes, so now you can see that the label has been dropped. Now it's time to do some feature scaling. Now our data is ready. Let's feature scale it from sklearn.preprocessing import standard scaler. Then we can do scaler equals to standard scaler, and then we do scaled x equals to scaler dot fit transform x. Remember that we don't have training and testing data. In unsupervised learning, we don't have anything to test against. Evaluation is a little bit more trickier. There's other ways to evaluate. We can take a look into scaled data like this. It looks like this now. We have scaled it. We can take a look into scaled x dot mean, and you can see that it's almost 0. It's basically 0. Scaled x dot std, and you can see that this is 1. Okay. Good. Now, let's take a look into sns.scatterplot x equals to scaled x of :0. Then we take everything from first column. Y equals scaled x of :, and then 1. And you can see that it looks similar as before, but the scale is different now. We have from 0 to around 1.6 and to -2 around. If you look back into the previous one, we have from -10 to 10, -10 to around 8 here. You can see that it still looks the same as before, but with other scale, because we have featured scaled it. Now it's time for K-means clustering. And for K-means clustering, we do like this. I'll show you the different steps. I explained these steps clearly in the theory section before, in a theory video. What you can see from here is that we choose k number of clusters, and then k points are randomly selected as cluster centers. Then the points to each cluster center are classified as the cluster, and the center of the cluster is recalculated. Repeat step 3 and 4 until it converges, basically. That is the idea. To choose k, we plot an elbow plot of sum of squared distances. This is inertia in sklearn, and find the inflection point to choose k, i.e. the point with significant lower rate of change than before. Then it's basically an elbow that you're looking for, an elbow plot. To do this in practice, let's do from sklearn.cluster import KMeans. Also, it's important that you should combine this together with domain expertise, that maybe someone knows that, yeah, the clusters should be between 5 and 8. Then you look into your elbow plot and see that, okay, here 6 was quite a good elbow, for example. And then you combine these two to choose. Okay, we start with fig, x equals to plt.subplots. This is plt sub+1, and we need to import matplotlib.pyplot as plt. For this, we do here clusters equals to range 1,10. Okay, let's try out KMeans for 1. KMeans, we have 3 as k equals to 3. Let's see if we can have n clusters, it's called. N clusters equals to 3, and then we have n init equals to 10. This means that it will do 10 seeds of clusters, and it will run it 10 times, and then we can take .fit, scaled x, and then let's see what we get here. We can see kmean equals to this one. Right now you can see kmeans, it just looks like this. Then we can do kmean dot inertia. The inertia is the one that we should plot. Inertia means within cluster sum of squares, or WCSS. What it means is that lower inertia, it means that the value indicates that the data points within each cluster are closer to their respective centroids. It means that it's more compact and better clustered. While higher inertia means that the data points are more spread out. It's less compact. That is what inertia means. As we have done this, now we know that we can plot the different inertias. What I will do is that I'll just print this out to see that you can see it. And actually I will remove this fig here. We can go into the next one. And to the next cell. Here I will plot it. Sum of squared distances, or within this WCSS, within cluster sum of squared distances, but I'll just call it sum of squared distances, equals to, we'll do k-means here, of k, n init equals to 10, then we'll do dot fit, scaled x, dot inertia, for k in clusters. And then you can see sum of squared distances, it looks like this. We have values that are high in beginning, and then it's going down. What we can do is that we will plot this now. x.plot, and we'll plotting sum squared of distances, and we will have, let me see what it was called here. We have clusters, comma, square, sum squared of distances. We can take a look into -o. Yes, that looks better. We'll have x.set, title equals to elbow plot to find k, x label equals to number of clusters, y label equals to within sum of squared to cluster centers. Okay, better. Okay, from this you can see that the rate of change is quite high here. The rate of change is high, and then it gets lower here, and then it basically starts to flatten out. For this, it's quite clear that we choose 4. Based on this one, we choose 4 clusters, and we can go on and take a look into silhouette plot. This is another way to take a plot to see the measure of cluster tightness. Note that it's usually not possible to plot clusters. Instead, the silhouette score in combination with elbow plot that we had before can help in determining the clusters. Silhouette score is a measure of the cluster's tightness. What you do is that you calculate the silhouette score for different k clusters. Then you take a look into the value. Silhouette coefficient is between -1 and 1. 1 means that it's very compact clusters. 0 is overlapping clusters, and -1 it's the opposite. It's the worst values. Okay, to calculate the silhouette score, we have from sklearn.metrics import silhouette score. Here we take basically same as before. Let me copy this one here. But instead of inertia, we'll just fit it like this. Then let's see, k-means of that one. We have k-means equals this. Then we will have silhouette list is then we'll do silhouette score. We'll do silhouette scored on scaled x, comma, k-mean dot labels underscore for k-mean in k-means. Then we'll take a look into silhouette list. We'll have x dot plot clusters from 1 and forward, and then we'll plot the silhouette list. Let me see. We'll do fig, comma, x equals plt.subplots of 1. Okay. Yes. Here you can see the silhouette. It's increasing for different clusters. Let's see. We have set title equals to silhouette plot, x label equals to k clusters, y label equals to silhouette. So it's quite hard to spell this score. Okay, here you can clearly see that number 4, we have the highest silhouette score, and which corresponds to what we had in the elbow plot, that 4 is the number of clusters to choose. Based on this one, we can make some plot to see how it looks like. After we have done our k-means, what you can do is that you can plot. We have df plots. I will call this, I will do a data frame here. We've scaled x columns equals to x1, comma x2. This is our df plot. It looks like this. We want to plot this one. We want to have fig, comma x equals plt.subplots 2, comma number of plots that we want to make. For example, I will make 4 here. I will have it like this, but I will change the fig size to make it a little bit wider. 16, comma 8. Yes, now I have my plots ready. For I, comma x in enumerate axis, let's see, you can call this axis dot flatten. I will loop through each of these, and then I will do cluster centers equals to k-means of I dot cluster centers. So I get each of the cluster centers. Then I will do df plot of, I will put in the label, should be k-means of I dot labels. This is the true label. Then I will do SNS dot scatter plot. Data equals df plot. X equals to x1. Y equals to x2. Hue equals to label, the true label. And x equals to x. Comma palette equals to tab 10. This is same as we've done before. But now, let's also, we will start with this one. This is all the classes that we have. I'll remove the legend. X.legend. Let's see. Yes, all the legends disappear. Okay, now I want to plot my scatters as well. I want to plot my cluster center. Cluster centers of colon, comma 0, comma, cluster centers of colon, comma 1, and I will change the size to 200, marker equals to star, color equals to black to see where it found its cluster center, label equals to centroid. This is where it found its cluster center. As you can see, in the 0, we have the cluster center here, and for the 1, and then 2, we have it here, and then 3 like this, and then 4, you can see it's perfectly for our clusters. Then 5, they divide here, and then 6, they divide, 7, they divide, etc. This is quite nice to visualize our clusters, and it's quite nice. We can actually do like this: x.set title equals to f-string I plus 1 clusters. Here you can see 1 cluster, 2 clusters, etc. However, note that in reality, when you don't have the labels, you cannot plot out the actual colors of it. And also in reality, when you have a lot of features, then you cannot plot it out like this. Because you could plot it out if you do, for example, PCA before, in order to reduce the dimensionality. You can do dimensionality reduction techniques in order to plot it, but otherwise you cannot plot it like this. This is just a simplified example where we have created the data through simulation. Okay, in this video we have gone through simulating data using Scikit-Learn's make blobs from datasets, and afterwards we plotted the dataset and we tried to do KMeans, unsupervised learning. In unsupervised learning we don't have labels, and we did use different methods to deal with that. We used the inertia to do an elbow plot, and then we used silhouette score, and we saw the knee plot. Then afterwards, finally we plotted out the data and took a look into the cluster centers. That was quite interesting to see. However, note that it's not always possible to do that, since in reality you may not have 2D data. You may have a lot of features, but if you have a lot of features, you could still do PCA for dimensional reduction. But I hope that you learned a lot from this video. Thank you, and see you in the next one. Bye.